Welcome in our lecture Fundamentals of Casting and Solidification. Now we are going to discuss lecture 8 Vertical Gating System. Before going to detail, in we have a last lecture we have understand the principles we are going to use for the gating design. In that terms they are called fluidity. Fluidity is a ability of liquid alloy and metal to flow readily in mold and to fill thin sections. Okay. It is ability to flow, measurement of ability of flow, how much length you are able to flow. Okay. Simple thing, measurement in casting. Okay. Fluidity is inversely proportional to viscosity. Okay. Fluidity inversely proportional to viscosity. If high viscous, low fluidity, low viscous, high fluidity. Okay. Fluidity is proportional to superheat. Means if molten metal is 700 degrees Celsius like aluminum, pure aluminum we are talking, what is superheat? 40 degrees Celsius, and you can take 760 degrees Celsius, 700 degrees Celsius, and this is 760 degrees Celsius, Tp equal to, and Tp equal to, in this situation where a higher fluidity 100 degrees Celsius, but there is a limitation, we will understand that. Okay. Fluidity is inversely related to temperature range. Fluidity is also dependent, inversely proportional to the temperature range. What is the temperature range? Is called liquidus minus solidus temperature. Liquidus minus solidus temperature we will understand in the alloy and solidification part. Okay. Currently we are not going to discuss in that, but you can I am just saying del T equal to T liquidus minus Ts. Okay. Del Tr is equal to TL minus Ts. If fluid is inversely related to the temperature range over which solidification occur, in pure metal and eustatic del Tr is 0. Okay. If is 0, so in that is called short fringing range, tends to 0. In short fringing range have higher fluidity, obviously 1 by del Tr, TL minus Ts are equal to 0. In this case TL and Tr are same, TL and Ts are mostly same. So, what happened, del Tr is going to be 0. In these situations what happened, have higher fluidity, obviously range has lower fluidity than pure material and or eustatic alloy. So, high surface tension of liquid metal reduce the fluidity. What if surface tension is high of liquid metal is high, which reduces the fluidity. Oxide film formation on the surface of molten alloy have significant adverse effect on fluidity. If any oxide is forming on the during the molten metal, which reduce the fluidity. Okay. Insoluble inclusion also reduce fluidity. Okay. And how we test fluidity is a spiral testing. How we test this is a spiral testing. There you can see the what happens in this, there is a scale have made. Okay. Something like this, marking will be a scale marking will be, length marking will be there. And we start filling molten metal in these sections. From there we start to pour and allow to fill the cavity, and if fluidity is perfect, you will see liquid reaching at the last point. If fluidity is not perfect, what will happen? It will stop like here. Before the last point it can freeze and we can't fill ahead. Okay. So, this is we can check how fluidity of the alloy or material, what is superheat is playing the role, what viscosity and all things can be checked by this. So, let us assume we can see the test low fluidity and high fluidity where some composition have changed, and you can see the fluidity is just, it is, you can see this length change, these points are visible, this scales, and this counting say what is the how much fluidity are there. Okay. Similarly, this figure A and figure B. So, figure A and figure B I can clearly say B as higher fluidity, you can see the length are till more length we are able to fill and allow to solidify, isn't it? So, we can say circuit B has higher fluidity than A. A longer spiral indicates higher fluidity. Any doubt? Okay. Now, based on that, we after the melting, metal is poured into and injected into mold cavity. Okay. Good gating design ensure distribution of metal in mold cavity at a proper rate without excessive temperature loss, turbulence and entrapping gas and slag. A good design should be without temperature loss, without turbulence, without entrapping gases and slags. Okay. If liquid metal is poured very slowly, very slow, let us assume we are pouring very slowly. Very slow means V is very less. What does mean? Reynolds number is very less. You are planning for laminar. Okay. Let us assume you are planning for laminar. Then the time taken to fill up the mold is rather longer, obviously. The solidification may start even before the mold has completely filled. Then what will happen if you are not filling proper slowly, you are trying for laminar, you are not want to go in transition region as well as turbulent region, means your Reynolds number is less than 2000, let us assume, then what will happen? There is chance that it will start solidification, okay, because it will take some time. After that solidification will superheat will complete lost by the cooling of mold wall. What will happen? Solidification will start. Then chance, what is chance? Maximum chance is there, you are not able to fill the cavity properly. Then if you are not able to fill, you are not getting casting, it will not going to sell, simple. Okay. So, what you have to do? You can't go very low velocity also, even you can't try for laminar. Okay. So, that is why I am discussing last lecture, your turbulent, you are not going to be extreme turbulent, but you have to go 2000 to 20,000 Reynolds number. Then this can be avoided by using too much superheat. You can avoid this thing, even you are filling a low velocity, then what can you do? You put high superheat, then you can achieve, then you can fill the cavity. But if a high superheat, what will happen? Then gas solubility may cause a problem. At high temperature, solubility is the main problem. Gas solubility is very high. Okay, that will understand after few lectures. Okay. Then what happens? If gas is entrapped, you will form oxide, and that has different mechanical property than basic casting. Okay. So, it is a problem. If you are planning for more high superheat, that is also a problem. Velocity is low, laminar kind of thing, that is also a problem. In other hand, if liquid metal impinge on the mold cavity with a high velocity, if let us assume you are planning to fill very fast, the mold surface may erode and sand will go into the casting, again problem will come. Thus, compromise that made of arriving in optimal velocity. So, you can't go very low, very high superheat or very high velocity. So, you have to optimize your velocity such a that the design of getting depends on both metal and mold composition. Okay. You have to optimize your design such a way that your design should be perfect to fill cavity as soon as possible without defect. Okay. Like erosions, you do not have to erode the mold surface edge. Okay. You do not have to entrap gas edge due to turbulence nature, something like that. You have to avoid such things. Broadly, gating designs can be classified into three categories, namely vertical gating, bottom gating and horizontal or parting line gating. You will understand this first. First is vertical gating. We are going to discuss today about vertical gating only. Okay. The vertical gating, liquid metal is poured vertically, we fill molten metal vertically to fill the mold with atmospheric pressure. What is the thing here? We fill the cavity in vertical gating system when our pressure is minimum at atmosphere. Gauge pressure will be 0, P equal to P atm at any place minimum. We have to ensure that throughout the filling pressure should be minimum P atmospheric or P gauge. Okay. Gauge pressure will be 0 or P atmospheric pressure, that is P gauge 0 means atmospheric pressure. Okay. In bottom gating, liquid metal is filled in the filled in the mold from the bottom to top, thus avoid splashing oxidation associated with the vertical casting. In last what happened, directly pour, some chances is there, some gases entrapment happen, oxidation formation happen. To avoid that, we do bottom gating. Okay. Okay, we fill from the bottom, slowly it will fill. Okay. In next lecture we will understand this. Okay. Third is horizontal or parting line gating. In this gating design, gates, runners and all gate are on the parting line of the casting. It is not about only cope and drag, pattern should be in cope and drag. Otherwise, if you are only cope, pattern you only drag, then you obviously top gating. It should be, your pattern should be in cope and drag, and your runner should be, or ingate should be in at the parting line. In the horizontal gating system, this is named as horizontal gating system or parting line gating system. Additional horizontal portion are introduced for better distribution of liquid metal with minimum turbulence. Okay. With minimum turbulence, we try to optimize. It is effect of both top gating and bottom gating. Okay, we will understand this as a example in numerical problem. Okay. Vertical gating system. Now we are going to discuss about vertical gating system and the pouring time. So we are assuming that this is pouring basin, this is sprue and this is mold. Okay. Pouring basin has PB, HB, height is HB, what is the sprue? HS, so it will have called HT, total height, and mold has height H. Okay. HM, we will write casting height is HM. So we will make 3 point 1, 2 and 3 points for calculation of pouring or time. Okay. We are calculating this. Okay. We are making 3 points and we can write equation. So first assumption, since what is top gating system, minimum pressure should be, filling should happen. At least atmospheric pressure. So P1 equal to P3 equal to P ATM. Okay. We are assuming that P1 and P3 are at same pressure. First, it is also assumed that level 1 is maintained so HB is fixed. HB, since what we are assuming that mold is filled, pouring basin is filled, so HB is fixed, it is not varying with the time. Okay. So if your HB is fixed, level 1 is fixed, what will happen? If you are maintaining the level, velocity will be, so at level 1 is 0. Any doubt? What we are assuming? First, what is the condition of top filling? All placed, minimum pressure should be atmospheric, minimum. filling should be not below the atmosphere. So, P1, P3 will be P atmospheric. Since level 1 we are assuming that it is a fixed position, it not varying with the time, okay. We are continuously pouring and we are maintaining the position of 1. So, what happens? What will happen? HB is fixed and as well as velocity is of this point is 0, okay. Now, 1, 2, 3, HB, HS, HT, HM. Okay, Bernoulli equation. Between 1 and 3. Fourth assumption is neglecting any losses, any frictional losses, we are going to ignore that, okay. Based on that we are writing that Bernoulli equation between 1 and 2, that P1 by rho g V1 square by 2g plus HT equal to P3 by rho g plus V3 square by 2g plus 0. We are assuming that I am playing here, okay. Potential energy, okay, pressure energy and kinetic energy, all three terms we have written for 1 and 3. So, P1 and P3 P ATM. So, they both can be cancel out, okay, both are same. So, cancel out. V1 is 0 because we are making the station is stationary, okay. Then what will happen? V1 will be 0. What is remaining? HT equal to V3 square by 2g, okay. Then V3 equal to root under 2g HT. V3 at the here, what is the velocity? Root 2g H2 free fall, okay. V3 2g HT. Any doubt? Okay. 1. And what is V3? V3 equal to velocity of in-gate. Here 3 is behaving as a gate, okay. Screw bottom is behaving as a in-gate. So, you can write V3 is Vg and that is equal to root HB HS HT 2d HT. Now, we know the velocity, we know the AG also, AG cross section area of in gate, we know that also, the area of in gate here, okay. Okay. Now, if we know the volume, if the volume flow rate at 3 position, 3 point, third point is equal to, at 3 equal to A3 into V3, A3 into V3, and that is equal to AG into Vg, that is equal to Ag, isn't it? You can write that. To fill the mold volume V time needed by in gate is Tf is Tf. If the mold volume, this volume V is equal to volume of casting, okay, casting, and then time needed by ingate is Tf. So, time to fill into volume flow rate of ingate should be equal to volume of casting, isn't it? Volume of casting. So, Tf into Ag Vag equal to volume of casting. Okay, Tf Ag into Vg. So, Tf equal to volume of casting divided by Ag Vg, volume of casting divided by Ag into so Tf, the time of filling time will be given by volume of casting is already known because you have already designed how much volume you have to cast, and divided by Ag, that is already known, the ingate area, divided by root under 2G HT. What is HT? Total height of the sprue plus basin, summation of HB plus HS. Okay. HT equal to HB plus HS, height of basin plus height of sprue. Okay. Based on that, we will solve numerical problem. Vertical gating system, we have one numerical problem, we will solve that and then we will calculate the filling time. Let us assume the gating design of mold of 50 cm into 25 cm into 15 cm. We have to cast this height is 15 cm, this is 25 cm, okay, and this is 50 cm. So, volume of casting equal to 50 into 25 into 15 cm cube. Volume of casting is 50 into 25 into 15 cm cube as shown in the figure. The cross section area of ingate is 5 cm square. The ingate cross section area is 5 cm square. The area is 5 cm square. So, Ag is given. What is Ag? Ag equal to 5 cm square. Okay, Ag is given and volume of casting also given. Now, we have to calculate Vg, 2G HT. Okay. So, determine the filling time for the gating design. So, which type of gating system is this? Top gating, vertical gating system. Okay. It is because it is a you can see here it is directly what is happening, we are filling at the parting line, you can see here, and they know any mold in the cope, in cope. What is happening? It is all things in drag and directly connected into atmosphere. Any place you go, the liquid is at minimum at atmospheric pressure. Okay, so we can say this is a vertical gating system. In vertical gating system, Ag is given, volume of casting is given. So what will happen? Vg equal to root under 2g ht. What is ht? Hb plus hs. What is hb here? Figure is showing 3 cm, hs 12 cm. So hs is 15 cm. So Vg equal to root under 2 into 9.81 into 0.15 or 2 into 981 into 15, that is in cm per second. We know in terms of cm per second. And now we calculate Tf. Tf equal to volume of mold, we know Tf equal to volume of mold divided by Ag into Vg, that is equal to 50 into 25 into 13 divided by Ag is equal to 5 into Vg equal to root under 2 into 981 into 15, which is coming to 21.86 second. Okay. So in top gating, what is the assumption? We have assumed that mold filling should be happen with at least atmospheric pressure. How can we know? You have to just check first, like in this numerical problem also, it is directly connect. Is there any mold on top? No. Above the pouring system or gate system? No. So it is a, and you check it's a top filling, top side, or like this. It can happen like this also filling. So this will call bottom gating. So this is not bottom gating also, it is looking like a top gating system. So top gating as a vertical gating system, in that you have to ensure that pressure should be minimum P atmospheric. Based on that, we have got calculation of Tf equal to volume of casting divided by Ag into root under 2g ht, and ht is the summation of pouring basin plus sprue height, total summation of this, and based on that, and we have solved this numerical problem. Thank you.